determining the AP from two given terms. Now, if you look back at our previous lessons, things were quite straightforward. We learned how to calculate any specific term in a sequence as long as we already knew the first term, which we call A, and the common difference, which we call D. Having those two pieces of information makes finding any term very easy. However, as we move into more complex mathematical problems and real-world applications, you'll find that life isn't always that simple. We aren't always handed the first term and the common difference on a silver platter. Instead, you will often encounter scenarios where you are only given two arbitrary terms from somewhere in the middle of the sequence. For instance, you might be told what the third term is and what the 10th term is, but nothing else. Welcome, everyone. Today, we are going to tackle a slightly more advanced topic, determining an arithmetic progression, or AP, when we are only given two specific terms. In the next few slides, I am going to show you the logical approach to using those two pieces of information to uncover the entire pattern. Conceptual approach. To determine the entire arithmetic progression, our primary goal is to find the values of A, which is our first term, and D, our common difference. Since we are dealing with two unknown variables, we can't solve it in one single step. Instead, we are going to use the general term formula to create a system of two linear equations and then solve them. As a reminder, let's look at the general term formula. The formula for the nth term of an AP is a sub n equals a plus the quantity n minus 1, all multiplied by d. This is the foundation of everything we are about to do. Now here is how we create equations from the given terms. When a problem provides us with two different terms, let's call the position of the first term p and its value a sub p, and the position of the second term q and its value a sub q. We can write two distinct equations. Our first equation will be a sub p equals a plus the quantity p minus 1 times d, and our second equation will be a sub q equals a plus the quantity q minus 1 times d. By solving these two equations simultaneously, and I highly recommend using the method of elimination here, we can isolate and find the values of d and a. Once we have successfully found these two values, the entire AP is defined, and we'll be ready to follow the step-by-step procedure shown on the next slide. Now that we've established that we aren't always handed the first term or the common difference on a silver platter, let's talk about our conceptual approach to solving these problems. Step-by-step procedure. Now that we understand the concept of using two equations to find our unknowns, let's break this down into a clear, step-by-step procedure that you can apply to any problem. Step 1. Your first task is to translate the word problem or the given information into mathematical equations. To do this, you'll use the general term formula, which is a sub n equals a plus, parenthesis, n minus 1, parenthesis, d. You need to apply this formula to both of the terms you were given. Be very careful here. Replace the a sub n with the actual value of the term, and replace n with its specific position in the sequence. Step 2. Once you've done that, you will have successfully set up a system of two linear equations. Both of these equations will contain the same two unknown variables, a, which is our first term, and d, our common difference. Step 3. Now we need to solve this system. The most efficient way to find the common difference, d, is to use the elimination method. Simply subtract one of your equations from the other. When you do this, the variable a will cancel itself out, leaving you with a simple equation that allows you to solve for d directly. Step 4. After you have found the value of d, you aren't finished quite yet. You still need to find the first term. To do this, take the value of d you just calculated and substitute it back into either one of your original equations. This will leave you with only one variable, a, which you can then easily solve for. Step 5. Finally, once you have both a and in hand, you have everything you need to define the entire progression. You can now write out the terms of the AP by listing the first term, then the first term plus d, then the first term plus 2 times d, and so on. In the next slide, we are going to put this exact 5-step process into practice with a real-world scenario involving a stadium seating arrangement. Real-world example. Now that we have gone through the theory and the step-by-step procedure, let's put everything we've learned into practice with a real-world example. Imagine a construction company is designing a tiered stadium. In this design, the number of seats in each row increases by a constant amount as you move further away from the field, which means the seating arrangement follows an arithmetic progression. The manager has provided us with two pieces of information. The fourth row has 150 seats, and the 10th row has 210 seats. Our goal is to determine how many seats are in the very first row and to find the common difference, which is the number of seats added each row. Let's break down the solution step by step. In step 1, we identify our given values. From the problem, we know that the fourth term, or a sub-4, equals 150. We also know that the 10th term, or a sub-10, equals 210. Moving to step 2, we need to create our equations. We will use the general term formula we discussed in the previous slide. A sub-n equals a plus the quantity n-1 times d for the fourth row. We substitute 150 for a sub-n, and 4 for n. This gives us 150 equals a plus the quantity 4 minus 1 times d, which simplifies to 150 equals a plus 3d. Let's label this as equation 1. Now, for the 10th row, we substitute 210 for a sub-n and 10. For n, this gives us 210 equals a plus the quantity 10 minus 1 times d, which simplifies to 210 equals a plus 9d. We'll call this equation 2. In step 3, we solve for the common difference, d. As I mentioned in the procedure slide, the most efficient way is to subtract equation 1 from equation 2. When we subtract the quantity a plus 9d minus the quantity a plus 3d, and set it equal to 210 minus 150, the terms cancel out. This leaves us with 9d minus 3d equals 60. So, 6d equals 60. Dividing both sides by 6, we find that d equals 10. This tells us the common difference is 10 seats per row. Next, in step 4, we solve for the first term. We can take our value of d equals 10 and substitute it back into equation 1. This gives us 150 equals a plus 3 times 10. Simplifying that, we get 150 equals a plus 30. By subtracting 30 from both sides, we find that it equals 120. So, the first row contains 120 seats. Finally, in step 5, we can define the entire arithmetic progression. Now that we have both the first term and the common difference, we can list the sequence of seats per row as 120, 130, 140, 150, and so on. Before we move on to the final summary, I want to point out a few common pitfalls to watch out for in problems like this. Common mistakes to avoid. First, a very frequent mistake is confusing the term position, which we call n, with the actual value of the term, which we call a sub-n. It sounds subtle, but it is crucial. Remember, n is simply the rank or the position in the sequence, for instance, the 4th or the 10th position. On the other hand, a sub-n is the actual number sitting in that position, like the 150 seats we saw in our example. If you swap these two when setting up your equations, your entire calculation will be incorrect. Second, watch out for sign errors during the subtraction step. As we saw in the previous slide, we subtract one equation from another to eliminate the variable a if your common difference, d, happens to be a negative number, which means the sequence is decreasing. You must be extremely careful when subtracting a negative value. A single misplaced minus sign here will throw off your value for d and subsequently your value for a. Finally, be mindful of incorrect substitution. Once you have successfully solved for the common difference, d, you must plug it back into one of your original equations to find the first term. Double-check your arithmetic during this step to ensure that you are applying the value of d correctly within the formula. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the method we just used in the stadium example, it is very easy to make small errors that can lead to the wrong answer. Please pay close attention to these 3 points. Keep these tips in mind, and you will find that solving for any arithmetic progression becomes much more reliable. Now, let's move to our final slide to summarize the key takeaways from today's session. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear. First, remember that an arithmetic progression is completely determined as long as we know any two of its terms. Even if we aren't given the starting point or the jump between numbers directly, those two pieces of information are enough to unlock the whole pattern. Second, the core of our strategy involves creating a system of two linear equations. We do this by applying the general term formula, which is a sub n equals a plus n minus 1d to both of the terms we were given. Third, when it comes to solving those equations, the elimination method is your most efficient tool. As we saw in our stadium seating example, subtracting one equation from the other is the quickest way to cancel out the first term and find the common difference, d, directly. Finally, once you have successfully calculated both the first term, a, and the common difference, d, the hard work is done. You now have the power to calculate any specific term in the sequence or simply list out the entire progression term by term. I hope this step-by-step approach makes tackling these problems much more manageable. Great job today!